networks
Recording
exchange
in progress.
information over public channels. It eliminates the need for physical access to their nodes. Also, without modification of hardware, attacks that leak information through set channels also becomes feasible through wireless networks. Based on this relatively easy access to the data, it becomes increasingly popular to target with wireless networks rather than the digital circuits. So now let's move to the basic idea of amplitude modulating analog RF hardware trojans. So as shown in this figure, the physical layer of a standard compliant wireless device consists of two blocks. The baseband processor is responsible for implementing the wireless protocol and its associated signal process blocks that convert the raw user data into a form suitable for transmission. The analog RF front end, on the other hand, plays a critical role in enabling the transmission and the reception of the transformed user data through the designated wireless communication channel. So in the analog RF front end, in particular, hardware trojans can exploit the margin we mentioned before to systematically modify the parameter of the transmitted signal, such as the amplitude, frequency, phase, or the combination of these three, to leak sensitive information from the target device. So what is amplitude modulating? The figure here on the bottom shows the comparison between the Trojan-free and the Trojan-infested transmission. The malicious circuit has embedded the leaked information in the transmitted signal amplitude while remaining compliant with the wireless protocol and the design specifications. So now let's just consider the following scenario. So Alice and Bob are two standard compliant wireless devices that have a legitimate communication established between them. And an attacker introduced a hardware Trojan circuit to Alice wireless hardware and systematically modifies the transmission power of the for the information extraction. So this process is not detected by the Alice. And at the same time, if the attacker or the third party observe this distortion and retrieves the leaked data. So the threat model here assumes that the hardware Trojan has been implanted either during design or during the ASIC fabrication of the transmitter, and that it can be used once the device is deployed. So the data leaked through the covert channel resides in the baseband part of the wireless device and is forwarded to the analog RF front end. Thus, this information bits are embedded in the transmitted signal through subtle amplitude modifications. So now let's discuss about like two examples for further explain about two types of blocks. So this RF or the RF Trojan, which leaks sensitive information to a ROG receiver through imperceptible variations in the transmit signal power. So for the RF Trojan, as you can see here, tolerance level in the form of return loss is provided in the ASIC specifications, which is used to account for imperfect impedance matching, which enables the data leakage by manipulating the termination impedance of the target IC by the attacker. As you can see here, by turning on and off these slightly different resistors, the input termination impedance is systematically altered, which further varies the power amplifier's input reflection coefficient and transmitted the signal power. And for the analog Trojan, information leaked from the baseband can be used to systematically modify the transmission power by exploding the gain stages because, like in the design of wireless devices, multiple gain stages in the transmission chain are needed to ensure the system linearity and the designed performance. As shown here, we can see the VGA here stands for the variable gain amplifier. The malicious entity systematically changes the VGAs to create variations in the transmission power in accordance with the leaked bits. So here let's discuss about the experiments and results of the attacks. So from two aspects, analyze the performance characteristics of the Trojans, and they're all like independent of the Trojan implementation from the paper. First, the paper shows the impact of the hardware Trojan operation on the legitimate communication. In the figure on the left, the PER stands for the packet error rate of a binary convolution code in a channel is shown for the Trojan-free and the Trojan-infested transmitter under different modulations as a function of the signal-to-noise ratio observed at the legitimate receiver. So we can see for 1 dB Trojan signal amplitude between the Trojan levels, a Trojan-infested transmitter will require more power to achieve same error probability compared with the clean transmitter. This is well within the variations introduced by the wireless channel and the device noise. Therefore, this Trojan cannot be easily distinguished from ubiquitous channel imperfections. And moreover, the observed Trojan impact is consist across modulation schemes and thereby verifying the robustness of the hardware Trojan attack. And second, the paper characterized the error probability of the Trojan included covert channel. So this figure on the right plot the error probability of Trojan communication. We can explore the trade-off between the Trojan transmission rate, Trojan probability of error, and amplitude of Trojan infestation. It is observed that the higher Trojan rates will either lead to more Trojan errors or require a larger amplitude modulation that would increase the probability of the Trojan being detected. And further, it indicates that reliability of covert communication is improved as raw data rates are reduced and as Trojan amplitude is increased. But the latter just come at the cost of the diminished Trojan inconspicuousness. And so next, my partner will introduce the corresponding defense mechanism the paper comes up with.
Okay, so before I start to talk about the defense mechanism introduced by the authors of this paper, I want to point out again that why the wireless network is so vulnerable to such attacks. So just like my partner stated before, there are certain inherent margins between the operating point and the circuit specs. So when the receiver observe a channel disturbance, it could either come from malicious Trojan activities, or it may come from channel 9 dialysis, like noise, interference, or the path loss and signal fading. So, a successful and effective defense mechanism must be able to separate this malicious Trojan activity disturbance away from the channel non-identity itself. So this is a comparison between the traditional channel estimation algorithm and adaptive channel estimation mechanism, which is proposed by the author. So in the traditional channel estimation, it assumes that the received signal is a linear function of the transmitted signal, and they are related by this channel matrix H, and the background white noise is represented here as an N. However, with the existence of Trojan hardware activities, this encoded data X is also scaled by this coefficient T, and this T represents the Trojan activities. And the significance of the ACE algorithm proposed by the paper is that this mechanism can actually distinguish H and T and detect the covert malicious activities. And this is a big picture of how the ACE works. It eliminates the noise and identify malicious activity in basically two steps. So in step one, it removes the Gaussian noise and basically the n term, so that we are left with h, t, and x using adaptive averaging. So because this noise is Gaussian normal distribution, has the Gaussian normal distribution behavior. So if we can take the average over an adaptive window, we are able to remove the noise, and that is represented in the step one on the left of the flowchart. And after we remove the noise term n, the next step is to determine h and t. So the way that ACE calculated h and separate h and t is that it first calculated h by computing the fading of the channel behavior and over a certain duration, and compare this fading of channel over time with the slow fading indoor model developed, which is developed as an very standard channel fading behavior. And by comparing the fading of the channel and the fading of the model, ACE can determine the edge of the channel. And after we know edge, we remove the edge from the equation, and we are left with the Trojan activity factor T, and we can tell whether the channel is being manipulated by Trojan activities or not. And this on the right of the flowchart is a heat map that represents the result of the Trojan detection. So ideally, if there is no Trojan activities involved in the channel transmission, after we remove H and the noise N, what we left should be the pure encoded data X, and it should be a uniform heat map. However, if there is certain Trojan activities being going on, the detection heat map have this non-uniform behavior. And this is a summary of the experiment that the authors have done. They have proved the ACE's effectiveness in multiple experiments, like line sight. Basically, when the receiver and transmitter they are placed next to each other. Non-line sight, when the receiver and transmitter they are separate, probably next door. And also under various Trojan operation characteristics, just like my partner explained, the Trojan activity may take place in the form of power, impedance, or gain, and all those different characteristics can be detected by the ACE at the receiver side, as shown in these figures. So in conclusion, wireless devices have these inherent margins between their operating point and the boundaries set by the designers. So, and this leaves room for the attackers to establish covert channel and undermine the security of the wireless devices and systems. And and we think the authors demonstrated the feasibility of RF analog Trojans in the context of wireless communication, and they successfully proposed a novel defense mechanism, ACE, and proved its effectiveness by various experiments. And lastly is some intuition we get from this research paper, and some possibilities we think that the future work could land. And after we read this paper, we found that this defense mechanism is very effective. However, it highly rely on the fact that the received signal is a linear function of the transmitted signal, and also this system specifically targets OFDM modulation techniques. However, as the communication the world of communication keeps evolving itself, our concern is that this ACE defense mechanism may not be widely applicable to other moderation techniques, and its feasibility might be undermined if by interferes, or if the environment gets more complicated, the function gets more nonlinear. Our concern is that ACE may not be very widely applicable in that case. And that's all we have for today. Yeah, thank you.
Thank you.
Can you hear me now? Oh, okay. Seems you can. All right. Any question? Just to confirm, can you hear me on Zoom?
Yes, we can. Yeah.
Okay, cool. All right. Any questions from the audience on Zoom or in class? Yeah, so the only thing, I mean, this was one of the examples of how realistic, hardware Trojans are and how we can actually implement them on systems. It could be on the actual processor or the memory. But this paper also shows that you can implement hardware Trojans in more advanced scenarios, such as like, in an actual RF transmitter or receiver. And then this way you can actually, exfiltrate some information and send out some information if you want to. Generally, again, as I said, this line of research has recently got much more popularity and much more attention, just because the fact that they showed that it's possible to use a seemingly innocuous and a normal device and show that this actually can leak information. And this kind of calls for fundamentally different ways of looking at how we build hardware and how we put our trust there. And given that hardware nowadays is being manufactured globally, then the problem of securing hardware is becoming more and more challenging. So we are kind of now dealing with this, the cost, the convenience that comes from the global manufacturing of hardware, but on the other hand, the problems that comes with it, right? Yeah, so this is kind of like, there are solutions like the one that has been discussed, but the real solution really is like, coming and building hardware components in a trusted fab. And where that trust comes in is a geopolitical issue. So it's something that's like even beyond something that we're discussing in this course. Okay, so let's go to the next. I think our next is actually in the class. Yeah. Even, are you gonna present? Oh, you okay. Sure. You want to use yours or?
No, it's okay. I'll just.
Oh, okay.
What's the easiest way to use?
The easiest way is you
Just leave it on. Just leave it.
we can I can just so is it just a video you're gonna play?
No, we're actually.
Okay, so let me give you this. That's actually no. Let's
Hi, Evan. Should I use my should I present the
Okay,
slide?
perfect.
I'll just do this that it follows you instead of me.
What do I have to do?
Yeah, that's the camera.
Oh, I see. Oh, cool.
Do your palms. Okay, wait for it. Wait for
Oh,
it to
sorry.
become green. Okay,
It locks.
there you go.
Oh, very cool. Go ahead. Okay, I think.
Oh, she's gonna.
Yeah, she's gonna share the.
Okay. Coco, are you there?
Yes. Sorry, give me 1 second.
Are you gonna share your screen?
Yep.
Can you hear us? Oh, okay, there you go.
Sorry, give me 1 second. Sorry, actually, can you share yours? Do you mind?
She's gonna, okay.
Should I mute first?
Sorry.
All right, go ahead whenever you're ready. Are you still there?
Yeah, sorry. Can you share your slides, Evan? I'm not sure how to.
She cannot. She
Oh,
cannot.
yeah.
Talk to this one.
Yes, I can.
Do you have Zoom on that? You can actually. Well, that's a technological nightmare of we have multiple microphones and all right. Yeah, just join as mute and
Yeah.
okay, awesome. All right, we're on. Are you gonna? Yeah, go ahead.
I'm so sorry, Evan. Okay, thank you. So yeah, I'm Rikako, and that's Evan in the class, and you're gonna present efficient hardware, malware detectors resilient to adversarial evasion. So can you go to the next slide? So here's a quick question for everyone. Have you ever been affected by a malware? You can type in the chat box, I guess. If you've ever seen like a bunch of windows in your screen and you can't really close those pop-ups, it's really annoying, right? Yeah, it's disgusting. So there's a bunch of series for a malware. It can be viruses or like adwares, as you can see. So if you can go to the next slide. So yeah, malware is still a major problem. I know this chart is kind of old, but malware infection rates are still increasing each year. And sorry, can you go to the next? Malicious attackers compromise systems to install malware. And since attackers find a variety of ways to obtain privileged access to systems, preventing the compromise of systems is practically impossible. And furthermore, modern malware is increasing in sophistication, making malware detection increasingly more complicated. So yeah, can you go? So traditionally, the malware detection was based on software, and there's majorly two types. So one is static malware detection and dynamic malware detection. So static malware detection is more of a signature-based approach, as where dynamic malware detection is a behavior-based approach. So what does that mean? Static-based approach searches for a signature, where unique identification of the malware binary file is searched without actually running the code. But on the other hand, dynamic malware detection involves observing the system calls invoked by the malware program during its execution in a closed, isolated virtual environment without proper monitoring so that it won't affect other systems. Since static malware detection scans for signatures but doesn't actually execute the code, different patterns are used to scan for these signatures, so they are effective against known malware. As on the other hand, dynamic detection involves a more thorough analysis, so it gains a better understanding of the malware and can work with all types of malware. However, each of these methods have their own drawbacks, where static cannot deal with new or advanced malware, and dynamic is more time consuming, and the overhead of analysis is large. So, in overall, traditional malware detection methods have limitations which allow attackers to remain undetected. And so in response to these traditional methods, HMDs, which stand for hardware malware detectors, were recently proposed to make systems more malware resistant. So recent studies have shown that low-level hardware features such as instruction mixes and memory reference patterns can be used to classify malware. And furthermore, machine learning can be used to detect anomalies, and HMDs offer a huge advantage to defenders because the detector is always on without having much impact on the performance and its power. So this is why HMDs are more malware resistant compared to the traditional software-based methods. So going on to the next slide. So there's two major contributions for this paper. So the first part, the paper explores whether attackers can adapt and create evasive malware to avoid detection by HMDs. And then if the answer is yes, then the second part, the paper investigates whether HMDs can be made resilient to evasive malware. So in the first part, the paper shows it's possible to accurately reverse engineer HMDs regardless of their complexity. And after the detector model has been obtained through reverse engineering, evasive malware is developed. And using these samples of evasive malware, it investigates whether the detector can be retrained to avoid them. And simple HMDs such as logistic regression cannot be retrained to detect evasive malware unless there's sacrifice on normal malware detection, but sophisticated HMDs such as neural networks can be successfully trained to detect evasive malware, although attackers can still reverse engineer to evade again, resulting in a cat and mouse game. So in the second part, the paper investigates if new HMDs that are both robust to reverse engineering and evasion can be constructed. And indeed, this is possible, and the paper proposes resilient HMDs, so RHMDs, which use diverse simple base detectors to prevent reverse engineering by randomizing detection responsibility. It also investigates switching strategies to maximize detection accuracy and proves that RHMDs do increase the difficulty of reverse engineering and complicate evasion, showing that they are a practical solution. So going on to the next slide. So why is this work significant is because in the past, there has been work on evasive malware detection in the context of software malware detectors, and there's also been HMD proposals that discuss the possibility of malware evasion, but this paper is the first to explore HMDs in detail and develop further solutions. So this work advances adversarial classification in any context and not just HMDs. And it also shows that systematically reverse engineering is possible, and developing techniques that use the result of reverse engineer detectors to efficiently evade detection is possible.
And then I'll unmute the mic. Okay. So I'm going to go into a little bit more detail about the methods that were used. And so the authors began with a threat model, which consists of an attacker who has black box access, to a hardware malware detector. And they wish to optimize their malware to evade detection while attempting to maintain the same levels of performance. And this last point is crucial because an attacker could always just write malware which proceeds very slowly, just operating like a normal program in between. And so that's a limitation of all anomaly detectors. But it's a reasonable assumption for time-sensitive covert or side channel attacks, as well as for computationally intensive attacks. So after defining that threat model, the authors needed to create some baseline HMDs. So they selected a training set from a mix of 3,000 malware samples and 554 non-malware programs. And they used linear regression and neural network classifiers for these HMDs, with each one of them using one of the 3 feature vectors that are listed here. Executed instruction mixes, so that would analyze which instructions and the frequency of instructions that are executed by the program. Memory access patterns, which would look at how memory is accessed. And then architectural events, which include things like taken branches. So the authors next demonstrate that an HMD can be reverse engineered by training a number of classifiers on the HMD's outputs for different potential collection periods and features. And so these collection periods would be how over what length of time the detector is gathering information in order to make that decision. And then the features are what we talked about before, looking at instructions or memory or other architectural events. And so then after training these classifiers on potential collection periods and features, we can compare we can see which one most accurately detects malware. And that was shown to be have the same collection period and features as the actual HMD that it was trying to replicate. And of the models tested, neural networks were able to best match the output or predict the output of target HMDs. So by examining the weights of the reverse engineered model, the attacker can then choose additional instructions to inject, which have the highest effect in causing the malware to be misclassified by the HMD. And 3 different methods of instruction injection were discussed, injecting instructions at the basic block level, at the function level, and then at a set interval based on a timer interrupt. And that one so they all were very effective. But the set interval approach had minimal overhead. So that was the one they went forward with. So to combat evasive malware produced this way, the authors first suggest just retraining the HMDs on this evasive malware. And so this successfully improves the classification accuracy on previous generation evasive malware. But then this reverse engineering and evasion process can just take place again. And so then you have this back and forth. And eventually, overall detection accuracy begins to drop for both regular programs and malware. And that's what we see in generation 7 here in this diagram. So instead, the authors present resilient HMDs or RHMDs, which are not subject to those same limitations. And RHMDs randomly choose between a set of different detectors with different collection periods and feature vectors, which makes reverse engineering substantially more difficult. And then a Bayesian-Stackelberg game was used to optimize the switching strategy of RHMDs for both accuracy and robustness, which resulted in opt-RHMDs, which used 4 of the 6 presented possibilities for detectors to achieve the maximum accuracy and robustness. So here you can see in the figure the probability that the RHMD will choose any one of these detectors in any given cycle. And so you can see in the opt RHMD, it actually chose to only use 4 out of the 6 because the other 2 were actually shown to either decrease accuracy or robustness in defending against evasion. So the results that they found, initially all of the baseline HMDs were able to achieve over 80% accuracy in detecting both malware and classifying non-malware programs. But with the evasive malware, that accuracy was decreased to below 20%, so very significantly. With this introduction of resilient HMDs, the accuracy again was able to again achieve an accuracy of over 80%. And then a further 40% was able to be gained by using the opt RHMDs. So 40% of that malware that was missed by RHMD was able to be classified correctly by opt RHMD. And finally, the RHMDs were shown to increase the area of an open source x86 SoC by approximately 1.72% and the power by 0.78%. So in conclusion, the paper showed that modern HMDs are vulnerable to reverse engineering and evasion. Retraining on evasive malware is ultimately an unsuccessful strategy. And so these new resilient HMDs use unpredictability as a defense against this reverse engineering and evasion. So we felt that the paper had a very strong motivation. Obviously, malware is something that is a very common threat, and software detection mechanisms often hurt performance quite significantly. And so again, with the discovery that it was so easy to reverse engineer the models that were used by these HMDs, they have a very strong motivation to propose these resilient HMDs. In addition, they have a very thorough evaluation of their RHMDs, including an examination of their malware detection accuracy, a formal proof of their increased evasion resilience, as well as an analysis of their contributions to SoC area and power. One thing that we thought was kind of a limitation was that threat model limitation that we talked about before, where the attacker could always just slow down their attack and have a lot of normal program instructions in between. And it would be very hard to classify it as malware correctly. But that's not necessarily a limitation of their approach. It's more a limitation of the overall strategy of using these features to detect malware. And for future exploration, one thing that could be considered is white box attacks. So in this paper, the authors only talked about black box attacks, and in that case, you would have to reverse engineer the HMDs. But with a white box attack, the attacker already knows all of the stuff that's happening in these HMDs or RHMDs, and so the improvement in making it difficult for them to reverse engineer these HMDs is no longer relevant if they know the structure of the RHMD to begin with. And so that's kind of another topic altogether that could be considered in the future. All right, thank you very much.
Any questions?
Yeah, this is.
There's something in the chat, I'm not sure.
Oh, yeah.
Open up.
It's just about the malware.
Yeah, so I mean, as you said, generally hardware malware detectors are one of these areas that got some popularity a few years ago. Then because of the limitation, it's kind of like, there were like lots of questions of like whether this is a useful scenario or not. But very recently, actually, Microsoft and Samsung, in their cell phone, Samsung and Microsoft in their systems, they started to employ hardware malware detectors. And that kind of like boosted the research in that domain one more time. But as you said, there are papers on kind of like, trying to criticizing hardware malware detectors generally because there is a lack of semantic between what is a malware and what is not. So for example, part of the malware could be, assuming that the malware is just some basic blocks, that basic blocks could also be present in any other legitimate programs as well, right? So that's the key challenge. And then the second challenge is the evasion, that either the malware could just hide itself under a legitimate program, or just generate some sort of like features, whatever that feature is, and just fool the detector. And so the research is kind of like in both of these directions of how to generate both resilient malware detectors and also kind of like add this notion of semantic to the execution, so we can kind of distinguish what is malware and what is not. But certainly it's something very useful and very helpful. And typically what happens is hardware malware detectors works as like a first line of defense, where essentially it's like, continuously scan through the execution. And then if something potentially malicious happens, it's just kind of like reported to a higher level, like a software level or operating system level. So it's not something that's, on its own make a decision, but you typically just send the information to one layer up. And there you can do more sophisticated, for example, malware detection and so on. So that's, but yeah, I like the idea of white box as well. Not sure how much work has been done on the white box. Brendan, do you know anything that's, white box? Have people look at the white box as well for evasion? Yeah, it's something to think about. That's interesting. All right. Yeah. Thank you. It's gonna follow you all the way. Interesting. That's a pretty accurate camera. I'm impressed. Yeah, it's go all the way. Wow. Anyway. All right, so who's next? Follow me.
I think we are next group.
Who is next?
The very sketch.
Okay, yeah, go ahead.
Screen files. Sure. Slideshow. So can you see that?
Yes.
So hi everyone, we are
Just one thing to mention that I think there is, since you're sharing your screen, there are things from Zoom that's kind of blocking it. There's something on the right and there's something on the top that's kind of like blocking it.
okay.
Yeah,
so
yeah, that window. Yeah.
Is that good? Or I need to like close the.
It's better now.
Okay.
Yeah, go ahead.
Okay, so we are introducing the very sketch, the synthesizing secure hardware design with timing sensitive information flow properties. And I'm Sumin Kao, and I will introduce the background and problem section. So what is the problem for our article? So the current problem highlighted in this article is the presence of security threats in hardware design. The present method applied in this case has been associated with security issues following their lack of frontline security approaches. And this could jeopardize the final design that a company develops. So further, this could give the attackers access to the critical information such as the user data and the privacy information. Thus, it could affect the credibility of the company and the success of the designs. Therefore, the current method of designing hardware are not up to standard following their failure to consider the security specification. Before we dive into the problem, I would like to introduce some background information about the what is the hardware design process is. And the figure shown on the slides is the typical hardware design process. First thing first, you need to have you need to know like what you want, and that is your specifications. Then you will try to create the whole system in the big picture, and that is the system level model. And then you need to do some RTL coding stuff. This is your RTL design, and this step will tell your software like your requirements, and after that the computer software will start to working on your commands. All you need to do is like debugging, and then the system level modeling and RTL design could be done by the engineers. But the third and the fourth step are too complicated for human to handle. And those steps will pass to the software to do, and that means it is semi-automatic. After all these steps, you will have your complete hardware design, and you can send it to manufacturers like NVIDIA and so on to like make your chip real. I think maybe 3 to 6 months your chip will be produced. And the prominent method of scheming digital circuit utilize the register RTL as the hardware description language, which is the register transfer level code. And for this reason, the designers are required to stipulate the micro architectural elements on the foundation of cycle by cycle completely. That means the complexity and the verbosity of RTL code could provide an opportunity for the security suspects and threats to hack into your system. With the increasing number of attacks related to the hardware security, there's an urgent need to enhance the framework for identifying and mitigating the suspect targeting on the hardware design. And to handle this situation, our very sketch is presented. So here's the flowchart for the very sketch. First, you need to draw the role sketch and set up the security constraint with its own syntax language. I believe you have read it, the related content on the article. And then the very sketch will run the constraint-based synthesis, which is this CGIS, the counter example guided synthesis method. If the result can pass all the requirements, it could generate a secure and correct hardware design. Otherwise, the designer will need to like modify the requirements such as the soft constraint and hard constraint to repeat the whole process. And then I will pass the presenter to Frank. He will present the rest part.
All right, so this is Han Yang. So I'm going to explain how VeriStack to VeriSketch to address the hardware security problem. So the traditional HDLs, such as like Verilog or VHDL, they don't lack a framework of capturing the security trace. And the information flow models enable the analysis of a wide range of hardware security properties. So the solution from this paper is using the tool IFT to define the labels of the variables to prevent the data leakage. For example, whether or not the variable contains a sensitive or an untrusted information. So IFT models capture how the data moves through the system, enabling the analysis of security behaviors of the hardware design. So next, the design is analysis to ensure that the public outputs maintain a low label, which indicates that no secret data has reached these ports. The IFT will annotating each design variable V with two different security labels, VS and VT, where the S labels track the logical flows and the T labels track the timing flows. So here we have an example from the paper. We can see that from the line 1 to 3 shows how to define the label of the variable stall. Two labels called like stall S and stall T. They are declared to track the logic flow and the timing flow respectively. So another thing need to mention about the IFT is that it will define the propagation rules for different syntax. For example, the propagation of the label of a variable which is operating in the non-blocking assignment is different from its operation in a blocking assignment. The goal of doing this is to make sure that the variable and their labels are updated simultaneously. And this enables to model labels and inference rules with standard Verilog syntax. So here's the formula of the propagation of blocking and non-blocking assignment. We can see that in the red box, it uses the blocking and non-blocking symbols respectively to match the Verilog syntax. And then I will explain about the logic flow, the logic tracking flow, the label VS, that how VS works in the IFT tool. So the logic tracking flow tracks both explicit and implicit flows. For example, the data path is tracked in the explicit flow and the control path is tracked in the implicit flow. And the explicit flow are tracked by instrumenting each operation, and the implicit flow is tracked by the upgrading the label by statement execution. So here we have an example of the explicit flow. So assume we have an operation that V equals to X bop Y. By using the IFT tool, this operation is tracked via GS equals to bop IFT parentheses X, XS, Y, and YS, in which the VS is the join of the XS and YS. And furthermore, the also depends on the Boolean values of X and Y at the same time. So let's take a look into the code. That we can see the operation is here in line 7, which is a non-blocking assignment defining the cache. And on the line 8 shows the defining of the explicit flow, and the line 9 defines the implicit flow in which the variable RD, RQ, stall, and the stall cycle, they are all implicit variables that can affect the variable cache. And then next I will explain about the timing tracking flow labeled in VT. The timing flows actually are a subset of logic flows, and which can be modeled by capturing how registers being updated at each clock cycle. To operate the timing flows, they use the syntax BALV to capture the changes in the design registers. So BALV is actually a Boolean variable that declares if variable V is balanced or not. A balanced update on BALV means that the value of variable V is stable and doesn't really change. On the other hand, the unbalanced update means that there is a clock cycle where V can be either maintaining its current value or get changed. So BALV is decided by announcing the program control flow graph. So here's the example of the timing tracking flow. The red box here indicates the timing flow that in line 3, we can see that it defines a label .t, and then between the line 10 to 10 to 16, it monitored by updating on the variables. And we can see that on the line 13, that the ball boolean operation is used here to detect the timing variable of the timing variation of the variable. So next, I'm going to transfer to Wayne to for the relation for the variation of this paper. Wayne, can you share your screen? All right.
Very good, Wayne. We cannot hear you. Wayne, you're still mute, or we cannot hear you.
We cannot hear you, Wayne. Can you raise the volume?
Yeah, I can hear
Okay.
you.
Okay, go ahead.
Okay, sorry about that. I don't know what's going on. Okay, can you see the screen?
Yes.
Okay. Okay, so I'm gonna talk about the experiments, and I'm gonna do a quick wrap up about what we have talked about. Okay. Wait a minute. Okay, I don't. Okay, it's working. So the authors demonstrate 4 examples of the security critical hardware designs that they have been successfully synthesized by their very sketch model. So basically, this table shows the code size for the biggest synthesized design in their experiment set. And those numbers are actually reported in terms of lines of code written in very sketch. And for the sketch and the specification. And so the first one, I'd like to talk about the arithmetic units. So I don't know how many of you have taken the M216 courses last quarter. So basically, we are using this Verilog syntax, assign C equals A divided by B. So we were thinking about, at that time, the professor provided us with a module that can do a divider and a multiplier. So we were thinking about why just don't we use the operator directly? So the thing is, when you're using this sentence in a always block, right? So basically, you want the RTL, you want the operators cannot be directly mapped to the hardware by EDA tools. Because this kind of assignments basically requires the EDA tool to build a divider which runs in a single cycle. So this is apparently not feasible in most cases. So we, as the hardware designers, we need to implement arithmetic units using these low-level operators. So basically, the one I presented here is the traditional shift and subtract. But actually, designing directly by this RTL, they will always lead to security problems. I'll just demonstrate it to you. So let me borrow this cute little figure from Professor's PPT. So basically, these arithmetic units, they run in multiple cycles. And so they could have like early termination based on the operand's values. Let's say this is A divided by B. So with different values of A and B, they can take different time to actually computes the value of C. And that way, if I'm the attacker using this the same cache, we're sharing the same cache, I can easily perform the digital side channel attack on the information on the A and B that I want to know, because you're using different time to compute, and this is a large information leak. So the way we can do with this, we can make it the multiplier to be time constant. So we can make sure whatever value we passed in, we always take the same amount of time to calculate. Okay, so now back to the flow that my teammates have talked about. So basically, we just talk about the sketch is the one we showed using the subtract, and the specification is the time constant that we want. Okay, so the soft constraints is something that can make the design a little bit better, but it doesn't always have to be satisfied. So then we input those things into the synthesis process. Okay, and then we can do the loop right here. So we do the verification, and then we do synthesis again and again, so that eventually we will reach a RTL design that is functional enough and also enough secure. So we use VeriSketch to design this fixed point multiplier, and it definitely runs in constant time, independent of their operand values. So basically, VeriSketch synthesized this sketch to a fully specified Verilog design that really meets the functional and security properties. Okay, so the other three examples basically follow the same method as the first one, but the author hopes to gain different insights from these three examples. So we use VeriSketch here to actually modify an existing cache implementation, such that it really defends against timing attacks. Timing attacks is the one that we just talked about, right? Maybe it's a side channel attack. So in order to analyze the effect, the authors simulate the caches which are synthesized with and without soft constraints using the memory traces from the Cloud Suite benchmarks. And so this is the figure that shows the eventual cache misses for simulating this four-way set associated caches of different sizes. And as you can see, all numbers here are normalized to the number of misses. So apparently, the lower the number, the better, because you want less misses, right? So you get more efficiency. So as shown by this graph, the cache which is synthesized with soft constraints has a considerably lower miss rate. Okay, next I'm going to talk about the design of a hardware thread scheduler for the multi-threading in mixed criticality systems. So for those of you who are not familiar with schedulers, basically they decide which hardware thread should execute at different clock cycle based on the inputs from the operating system. So this is the result that actually this result is not presented in the paper, because this is actually a drawback for the projects that the authors have conducted, because this actually shows, so you can see the axis is in the log scale. So the difference might seem little in this map, but it's actually really huge in the time difference. So the horizontal axis are different synthesis sizes, the actual amount of bit that we need to synthesize. And the vertical axis is the synthesized time. So it's the color represent the type of soft constraints that is applied to this design. And so as you can see right here, the gray bar only have like the hard constraints. So they have no soft constraints. And the yellow bar means efficiency soft constraints, which means that a thread will not be scheduled if they are not active. Okay, so the red one means that there should be two threads, and if they're in the same priority, then we should let them to take the same time in the core. So as you can see that those soft constraints do provide a better functionality, but the cost of the synthesized time is huge, and it's really more difficult. The more difficult the soft constraint, so the more constraints we want, the higher the time cost is. And also, as you can see, the larger the design, the more bits we need to design, the more effect having a soft constraints will have. All right, finally, I'm going to talk about a little bit pros and cons that this project have. This is what we believe. The author only talked about one side drawbacks. They think that it's better to use the max stat synthesis instead of a linear search, because they think it will be more effective for them, so that maybe this can help alleviate the problem of the synthesis time. So the pros are really evident right here. They really shorten the design period for hardware design. And also importantly, they make sure that the enforcement of security properties. And when we think the other drawbacks at first, that we think this is only half automated. It's not total automated. So it requires a lot of work during sketching and also creating those soft constraints by ourselves. So maybe those processes can be automated as well. And also, as you can see in the previous figure, so we have like a huge scalability issues right here. So if you have like a larger design, then it's harder to really implement this kind of error sketch model in the design. Okay, that will be all. Thank you.
Thanks. Yeah, this very sketch is actually one of the first papers in the realm of using tools for verifying security of the system, including like side channels or various various vulnerabilities that we discussed in this course extensively. The idea is that how we can use traditional verification tools that we usually just use for correctness issues, so making sure that there is no bug in the design and so on, and how we can extend this into also including things like various side channel attacks or various security attacks and so on and so forth. There are actually a large line of research and works that comes after this paper in just very few recent years. That's because this paper is kind of relatively new. I think it's published in 2018 or 2019, which kind of like tries to improve upon what's discussed in this course in this paper. And Wayne also mentioned at the end kind of looking at scalability issues. So there are like new ways of using things like fuzzing in order to have a better coverage and increase the number of tests and so on and so forth. So this is actually kind of like one of those areas that there are lots of people thinking about and working on it. And it's quite interesting because, again, this is kind of also a testament to what we discussed in this course, that security has always been, a secondary consideration, and then we always worried about, for example, the correctness, which obviously is a very important thing to consider as well. But nowadays, since security also has become an important metric, now you see that the same tools that we use during the development now has this additional feature, for example, for testing security and so on. So that's the idea. All right, so let's have a 5-minute break and come back at 3:27 and then have the rest of the talks. We have 2 more, I guess. So. And whoever is next, could you please, prepare, start sharing your slides and so on. All right, guys, please go ahead.
Okay, hi everybody. I am Hyomin An, and I am with my partner Armin Sategi, and we will be going over the Enhancing Power System Cybersecurity with Systematic Two-Stage Detection Strategy paper. Now, in 2015, a cyber attack against the Ukraine power system led to a blackout. This was the first successful cyber attack on a power system. The power system, being a cyber-physical system, is prone to false data injection attacks like the ones we have learned about in class. We'll go over into how these attacks work in later slides. Anyways, with such attacks, when successfully implemented, these attacks can cause blackouts and vast economic damage. Additionally, with more and more attention being given to ways we can reduce our greenhouse gas emissions, this brings about the need for technologies like increasing renewable energy sources, especially in residential areas, EV charging stations, smart homes, and etc. And as these newer technologies are driven with so much information technology, with so much information being processed in real time, and our global energy consumption constantly increasing, the cost of withstanding a breach in cybersecurity of the power system will only continue to grow. I know many of you may not be too familiar with how our power system works, so I will give you a brief introduction to power systems, describe what state estimation is and why we need it, and then go into how false data injection attacks work. So I find it easy to imagine our power system as a system of water. A waterfall or a generator supplies power to the entire system, and powerful upstream rivers or high voltage transmission lines send water over long distances. When we increase the voltage, we increase the current, resulting in lower losses during transmission, and that's why we have these very large high voltage transmission lines to do the bulk of our sending across large distances. After we get to the broader regions that we need, a complex web of low voltage distribution lines send power to industrial and residential loads. These are analogous to small streams that branch out from rivers to send water to be used by plants and animals. And yes, I did draw this picture because I felt we need to use good visuals. Here we have what our power system looks like. One very important fact to remember is that electricity cannot be stored in large scale. Yes, people say that large scale batteries can be a solution, but batteries are not economic to use on a large scale and probably never will be. Thus, the load and generation must be matched in real time by the system operator. To do that, the operator must know exactly how much power to send to each section of the grid. However, the power system is incredibly complex, so we cannot measure each voltage, current, and phase at each branch and node to give us such a detailed picture. This brings us to the concept of state estimation. Although we cannot measure all electrical quantities throughout the entire power system, given a state or the minimum amount of independent variables, we can find all other variables as dependent functions. You can kind of relate this to the states and state variables we learn in linear algebra. This state can be estimated with measurement values of power and voltage coming from local control centers and SCADAs. SCADAs stand for supervisory control and data acquisition. Just think of these as very big and complex tools that monitor electricity at various points throughout the power system. Like it states on the slides here, this state estimation is performed using measurements of power, voltage, and currents, and sending these measurements to an operator that performs the analysis. And this final state information is used by the system operator to provide real-time functions like contingency analysis, run economic dispatch, optimal power flow, and a variety of different functions we use on our power system to keep things safe and efficient. So this brings us to false data injection cyber attacks. We said that state estimation and ultimately the power flow in our system is determined in real time by various measurements. However, people with malicious intent could stage an attack by injecting false measurements in an unobservable way to corrupt SE solutions or state estimation solutions. This is called a false data injection cyber attack. For example, if we had malicious people from USC that wanted to turn off the power at UCLA, they could probably mess with the power measurements that go and come from UCLA to get UCLA all blacked out. Anyways, these erroneous results, these erroneous measurements result in state estimation that cause operators to make false and dangerous power dispatch decisions. This is why we must address such vulnerabilities. Currently, such defenses are divided into detection methods and protection methods, and this literature focuses on detection. The paper presents a method called the two-stage FDI detection, or the two-stage false data injection detection. The paper presents two metrics that are pivotal in detecting potential FDI cyber attacks, and they are BORI and MLDI. BORI stands for Branch Overload Risk Index. And this index monitors suspicious change in branch flows and identifies potential overloads. We also have MLDI, which stands for Malicious Load Deviation Index. And this index recognizes load change patterns and identifies malicious load deviation. The use of these metrics allows us to determine if a specific branch is a targeted branch of a cyber attack. So the first metric we will cover is BORI. A person with malicious intent could unnoticeably switch the measurement values for state estimation and cause overflow by having the operator shift loads. BORI is a value we use to measure the risk of branch overflow. To go over the equation really quick, Pk minus is the actual flow on branch K at time equals negative delta T. And that value is put into a sign function. To refresh your memories, the sign function has a value of -1 for negative inputs and +1 for positive inputs. PKOM is the measurement of flow on branch K at T equals, at the time equals negative delta T. And PK plus SCED here is the measured scheduled flow, is the scheduled flow on branch K at time equals delta T. And this is determined by security constraint, the economic dispatch at our initial time. The limit K here is the thermal limit of branch K, which is determined by the physical properties of the branch. We obviously don't want to overload our transmissions lines with too much current, or it may cause physical damage. And after calculating the values for BORI 1 and BORI 2, the BORI value for branch K is determined by taking the maximum between the two BORI values. And so this paper presents an alerts table based on the calculated values of BORI for a branch K. So if the calculated value we found here was over than 115%, it would correspond to a very dangerous level of power flow, and a BORI of less than 105% would be normal, and we would not see our situation as dangerous. The next metric presented is MLDI. MLDI is what can be called a power transfer distribution. MLDI is what can be called a power transfer distribution factor, which is basically a sensitivity factor that measures the incremental change in branch flow. MLDI is calculated as follows. PK negative is the actual flow on branch K, as we previously explained, and the indicator K and NLK values are defined below here. So this indicator function is used to indicate how much potential a certain branch has for overflow. DNOM, we see on the numerator term, is the load measurement at bus N, and DNO is the actual load. So the term we have here is a normalized error term. So basically, if the normalized measurement error of load is less than -5%, we assign PTDF to a negative sign function. And if the normalized measurement error is greater than 5%, we assign it to a positive sign function. If the percent error is small, as in less than 5%, we assign a value of 0 to the indicator to show that the branch of concern is relatively secure. MLDIK values range from -1 to 1, and higher positive values correspond to an abnormal fluctuation in load. This signals a high probability of branch K being attacked. Although MLDI itself can act as a metric to detect FDI cyber attacks, it fails to account for load magnitude and actual PTDF values. It merely accounts for the polarity of PTDF. So a third metric called the Enhanced Malicious Load Deviation Index is developed to account for these factors. To find the EMLDI, we add together the indicators for each branch with a weight that is found below. The weight W and K is called the influential factor for branch K due to the change in the load at bus N. Like so, EMLDI may make it easier to determine whether a specific branch K is in danger of being attacked. As can be seen in the table, the alert criteria for EMLDI is the same as that of MLDI. And from here on out, I will be switching over to Armin.
Hello. So Hyomin basically went over the background and the problem at hand in the paper. I'm going to be going over the solution and the evaluation of the approach. So to counter FDIs, the paper proposes the two-stage FDID approach. For this approach, various metrics are introduced to quantify the threat level throughout the transmission system, namely the system-wide malicious load deviation index, which stands for, which is SMLDI, ALB, which is the alert level associated with BORI, ALE, which is the alert level associated with EMLDI, and the metric ALC, which combines the alert levels of these two. And lastly, the comprehensive attack index, the CAI, which considers both load deviation patterns and potential branch overloads. So the first stage mainly utilizes MLDI and BORI to detect if there's an FDI cyber attack on a specific branch. This stage is mainly just to detect if there's an attack, and using the MLDI, using the average of the 10 branches of the top MLDI values, the SMLDI is obtained, which the system uses basically to determine if it's being attacked. If the SMLDI value is less than 35%, meaning it is at the monitor or normal alert level, the system is deemed free of FDI cyber attacks. Meanwhile, if the SMLDI value is more than 35%, meaning it is at the warning or danger alert level, the system is sent to the second stage of the approach to find the target of the FDI cyber attack, which moves us to the second stage. So once a case is sent to the second stage, the ALC and CAI are used to identify the target branch. As mentioned, ALC is the combination of the EMLDI and the BORI alert levels, and CAI, the comprehensive attack index of a branch, is the multiplication of the EMLDI and the BORI indexes for a specific branch, which indicates the possibility of a branch being targeted. Branches that either have ALC level of danger or a CAI ranking in the top 3 are considered the most suspicious target branches. To show the effectiveness of the FDID metrics and the two-stage approach, the proposed method was evaluated on 3 different systems: the IEEE 118 bus system under 3 different configurations, which enabled the approach to be tested for the effect of load fluctuations on FDI cyber attacks and the detection under different grid configurations. The IEEE RTS 96 system, which is a commonly studied test system with 73 buses, and lastly, the Polish system, which has 2,383 buses and highlights the robustness of the two-step approach. So after going through the evaluation, the results highlighted 2 key points. One, that load fluctuations or noise doesn't affect a FDI cyber attack or alter it in any considerable manner. And two, that even with load fluctuations present during evaluation, the two-stage approach is able to detect FDI cyber attacks. Additionally, it was shown that the approach can be generalized to all systems as it was successful under various configurations, as well as the polar system, which required monitoring of many buses at the same time. Some consideration for future work. One thing to consider for the future would be to make the approach also applicable with AC transmission systems, which would be very beneficial for industrial practices. Another thing to consider is to add more stages to the approach, perhaps make it a three-stage approach, with the third stage detecting the tampered measurements and determining an optimal solution to the issue. And as a final thought, many solar panels and residential battery power systems are being installed into the distribution system today. So this leads to power flow and distribution systems to be highly volatile and more prone to FDI attacks. Therefore, we thought creating a similar detection scheme instead of doing it for the transmission system, doing it for the distribution system would be very desirable. And that concludes our presentation. Thank you for listening.
All right, thanks for the great presentation. Certainly different flavor of what we had so far in the class, but it's also showing that, you know, when we are talking about cyber physical systems, right, we are talking about, you know, variety of different systems. Could be an autonomous system, it could be a power system, it could be a small and tiny IoT device, and so on and so forth, right? So essentially all of these different systems are vulnerable to various attacks. And when we're talking about critical infrastructure such as the power system, then things becomes even more serious, because essentially change will have a much more bigger and significant impact. Any questions, anybody? And thanks for the paintings, actually. Good job on those, Human.
Thank you.
All right. So we don't have much time left. We have one more talk. Unfortunately, since I came late, we lost some time. So here's what we're gonna do. We're gonna, I mean, the link is already shared on Zoom. So those of you who are on Zoom and have time, please watch it now. I'm gonna repost this Zoom link again on Campus Wire. So just please watch it in your own time. And this is also a very interesting paper. Just one thing is that this is not the paper on the paper list. It was the different papers because the presenters, for some reason, I mean, they decided to present something else. But just, you know, try to watch it, please. It's important and interesting. And since we don't have time, I just don't want to cut it off in the middle. All right, so that's it for today and for this class. Actually, I think this is our last session. A few things to remember. One is I think still we are at like 60% on the feedbacks. So please, if you haven't done so, or if you know your friends haven't done it, I don't think we have much more time left. I think it's the deadline is Friday or something. So just make sure that you submit your course feedback. That would be very, very helpful for us for next offering of this course. Projects due next Friday. The third quiz, if you're planning to take the third quiz, it would be starting on Wednesday and then it's gonna end on Friday. Probably just gonna, like, you know, go through everything the weekend after, and then sometime the week after I'm gonna release the grades. If there's anything missing or there's any problems in your grading so far, let me know, send me a message. If, as I said, if any of those paid projects that you're doing seems interesting and you think there's potential for, like, you know, build upon it and continuing, I'm absolutely interested to work on you with that. So, you know, reach out to me probably after you submitted your reports. For submitting your reports and videos and everything, I'm gonna post a link, a shared folder. Please put your shared folder there. I'm gonna just give you the instructions of how we're gonna do that. So just to keep an eye on the post on campus where of how to upload things and so on. All right. So I guess that's it. Thank you so much. It was a great quarter. I mean, we had lots of things starting with remote and then in person and all those things. But I think it was I think this was the second time I'm teaching this course and certainly a better experience than the first time, and hopefully it's going to be getting better and better. We covered lots of different things and probably may not catch all of that, but general knowledge of all those different layers of stack and what's going on in each layer, what is important these days and so on. That was the main goal of the course, and also getting some knowledge about and some awareness about cybersecurity and where we are headed. That was the another intention of the class. So hope you enjoy it, and if you have other friends next year, we're gonna offer it again. So if you want to recommend it to other friends, please do that as well. So thank you so much, and see you soon. Yeah.
Thank you, Professor.
Yep. Thank you guys on Zoom too.